band stop Butterworth filter. Okay, band stop Butterworth filter using the specifications given. Okay, so first specification is given as stop band attenuation or stop band frequencies at stop band is from 100 to 600 Hz. Okay, and second specification is given as 20 dB attenuation, 20 dB attenuation at 200 and 400 Hz. Okay, third, passband attenuation, passband attenuation is equal to 3 decibels. These are the details given in the question. Okay, so we have to design a what is given in the question. That's the first thing we have to check it out. What is given in the question? We have to design a band stop filter. We have to design a band stop filter. Second thing, it is a Butterworth filter. That's the second detail that is given in the question. Okay, what are the other details given? Stop band range is given. Stop band range is from 100 to 600 Hz. Okay, which means that the lower value is 100 Hz and the upper value is 600 Hz. Okay, this is the meaning of stop band 100 to 600 Hz. Second, it is given 20 dB attenuation, 20 dB attenuation at 200 and 400 Hz. Okay, so this will give you the information as alpha S is equal to 20 dB and these values are omega 1 is 200 Hz and omega 2 is equal to 400 Hz. Okay, this is the second piece of information you get. And third line is passband attenuation is 3 decibels, which means that alpha P is equal to 3 decibels. Okay, so these are the information you have. Omega L is 100 Hz, omega U is 600 Hz, omega 1 is 200 Hz, omega 2 is 400 Hz, alpha P is 3 decibels. We have to design a band stop, we have to design a Butterworth filter. Okay, these details are given from the question. Now, based on the given details, okay, I'm just constructing a small diagram just for understanding, or we can even do it without going with the diagram. So this is just for an understanding. I'm just creating a frequency response curve. Okay, so my Butterworth filter will have a very flat passband and a stop band. It will not have any ripples. If it is a Chebyshev filter, you're going to consider some ripples. Okay, so this is my flat passband and stop band. So as per the question, so this point, okay, so this is given as 3 decibels at alpha passband attenuation is 3 decibels and the range is from 100 to 600 Hz. Second, it has a stop band attenuation of 20 decibels at 200 and 400 Hz. Okay, these specifications are given in your question. Okay, I'm just drawing it as a figure, just you can visualize how our band stop filter should be. Okay, so given this, so what should be the first step? Remember, so first you have to calculate something called as A. You have to calculate something called as A. Okay, so A is given by omega 1 into omega u minus omega L divided by minus omega 1 square plus omega L omega u. Okay, so from our question omega 1, so first thing, everything is given in terms of frequency. Okay, so we'll convert this into omega 1 is equal to 2 pi into, okay, so f1, it is actually these are not omega, these are all frequencies actually given, it is in hertz. Omega unit is in radians per second. Okay, so omega 1 is 200 actually, so f1 is 200, so into 200 you will get it as 400 pi radians per second. Okay, similarly omega 2 is equal to 800 pi radians per second. Similarly omega L is 200 pi radians per second. I'm just multiplying these values by 2 pi. Okay, omega u is 1200 pi radians per second. Okay, so these values are actually FL, FU, F1 and F2. These are the things originally given. Okay, now we'll use these values in our problem solving. Here it is 400 pi into 1200 pi minus 200 pi by minus 400 pi whole square plus 1200 pi into 200 pi. Okay, if you actually solve for this, you will get it as 5. Okay, so second one, you have to calculate the value of b. B is given as omega 2 into omega u minus omega L divided by minus omega 2 square plus omega L into omega u. Substituting the values, omega 2 in our case is 800 pi. Okay, omega 2 is 800 pi, so 800 pi into 1200 pi minus 200 pi by minus 800 pi whole square plus 1200 pi into 200 pi. Okay, if you actually solve for this, you'll get it as minus 2. Okay, now we know the values of a and b. Second step, you have to calculate what is omega r. Omega r is nothing but minimum value of magnitude of a and magnitude of b. Okay, so minimum value of magnitude of a is 5. Similarly, magnitude of b is minus 2. So what I mean by magnitude, you need to drop off the signs. So minimum of 5 and 2 is 2. So omega r is taken as 2. Omega r is taken as 2. Okay, with this value we have to proceed with our design. Now we'll go with the Butterworth filter design part. Okay, so for Butterworth filter design part, so we have to calculate first the order of the filter. Okay, so the formula for n is greater than or equal to log of square root of 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 divided by log of omega c by omega p. Now the important thing to be noted here is this omega c by omega p is nothing but omega r. This is nothing but omega r. So accordingly n should be greater than or equal to log of square root of alpha s is given in the question 20 dB. Okay, so it is 10 square minus 1 divided by 10 power 0.3 because alpha p is 3 decibels by log of omega r. Omega r is nothing but the previous step we found it as 2. Okay, just substitute it as 2. Okay, and if you solve for this, n will be greater than or equal to 3.32. So we can round it off to the next highest integer, n equal to 4. Okay, so we found the order of the filter as n equal to 4. Okay, once you have found n equal to 4, you need to find the poles of the transfer function. How will you find the poles? Sk equal to e power j 5k and 5k. Okay, you can calculate using pi by 2 plus 2k minus 1 into pi by 2n. Okay, so for our case, k runs from 1 to up to n. In our case, n equal to 4, n equal to 4. So you have to find 4 poles. Okay, so phi 1, phi 2, phi 3, phi 4. Okay, so phi 1 is pi by 2 plus you'll get pi by 8. Okay, so this is coming to 5 pi by 8. Okay, similarly you have to find phi 1, phi 2, phi 3, phi 4. Okay, once you have found the 4 poles, 4 values, you need to substitute into sk and you have to find. Okay, I am directly giving you the analog transfer function. So there is a separate video how to calculate the analog transfer function. You can just refer to that video. Okay, so here we have to calculate sk, and sk actually comes to s square plus 0.765 s plus 1 into s square plus 1.848 s plus 1. Okay, so this thing we have to get it. Analog transfer function, you have to get it. Okay, once we get this analog transfer function, this one is whatever we have got is for the normalized frequency omega r, we have got it. Okay, this we have to convert into our band stop specifications. Okay, how will you do that? So for that you have to calculate something, S formula. Okay, S into omega u minus omega L divided by S square plus omega u omega L. Okay, this S you have to substitute into your H of S. That's how you convert the given transfer function which is normalized for omega r into our band stop specifications. Okay, so if you solve for this, this is 1200 pi minus 200 pi, so it is 1000 pi divided by S square plus omega u into omega L is 24 into 10 power 4 pi square. Okay, so wherever you have S, you need to replace by this value. So we'll take our H of S. So H of S is equal to 1 by, okay, so it is S square, so S into 1000 pi by S square plus 24 into 10 power 4 pi square, this square plus S into 1000 pi by S square plus 24 into 10 power 4 pi square into 0.765 s plus 1. This is one equation. Similarly you will have another one. So we will have s into 1000 pi wholes by s square plus 24 into 10 power 4 s plus pi square whole square plus 1.848 into s 1000 pi divided by s square plus 24 into 10 power 4 pi square s. Okay, I have put the s already. This is 1.848, this s plus 1. Okay, so this is your final H of S for your band stop filter. Okay, so this is how you design your band stop filter. So what you have to do, so first take out the specifications. From the specifications, find out A and B, find the minimum value of it, take it as omega r, magnitude of it. Okay, once you have omega r, substitute in the formula and calculate the order. From the order you find the poles, then you find your analog transfer functions. After you find the analog transfer function, find this value. Okay, this you have to substitute into your analog transfer function to get the analog transfer function for our band stop filter.